Well, tomorrow we have our test over this wonderful unit. Yeah? No? Maybe not so wonderful. Lots of different topics. Somewhat the same basic principle, but going in a lot of different directions here. So we'll talk a little bit of the details. We worked through basically all of chapter 7 and 8 in the Think Well material. 7.1 we covered and threw it in test 2. So 7.2 through the end of chapter 8 in the Think Well material will be covered on here. And because all of these problems tend to be fairly lengthy, we'll not have 20 problems on the test, but there's going to be 13 problems on the test. So each one be worth more points overall, but the test also typically runs a little bit longer. You may want to give yourself a little more time on this one. I'll be in room 101 from 9:30 to 10:20 tomorrow, and if you want to come in and get started early, or if you want to stay late, that's fine as well. But most students take around an hour and a half on this test, so plan accordingly. Some students get it done in 45 minutes to an hour. Some take a little longer. I've had a few that take way too long, but that's usually because they're not quite ready for it and they stare at a problem for 30 minutes. But of course, none of you will do that, right? Okay. But 13 problems. We'll take a look at what to expect. Way back in 7.2, I know that's been a long time ago. Spring break in this probably doesn't help either. But in 7.2, we started talking about the uses of the derivative. And one of those uses was to approximate a value. Linear approximation, I think, was the particular topic we used. And that was essentially taking something like approximate 1/2.2, okay, using a nice value, as I call it, rather than 2.2. So to get an idea of how to work through this, linear approximation, we look at the function. What function would be dealing with here? Okay, 1/x. And what's our nice value? X or A or C, whatever. What would our nice number be for this? Okay, 2. And then also use delta x. Delta x would be what? Okay, 0.2. Now, delta x would be the given value minus the nice value. Now, had this given value been, say, 1.9, then delta x would be what? We'd still use 2 as our nice value, but delta x would be negative 0.1. We'd have to take whatever this value is minus our nice number. So you could get a negative value for delta x. Okay. Well, going through this then, the approximation we would say is, let's see, the function value for our nice number plus, now this is where we use the derivative part. What do we do to the derivative? We'd have the derivative value at our nice number times what? Okay, times the delta x. Okay, so that will take care of how far away from our nice value we are. But our derivative f primed of x would be what? You know that one by heart by now. Remember, we'd have to say x to the -1, derivative would be -1 x to the -2, or -1 over x squared. And, okay, so 1 over 2 plus, well, f primed of 2 would be -1 over 2 squared, and then times 0.2. And let's see, various ways to think about this, but we can look at the decimal values if you want. 1/2. Now in this case, we'll end up with a minus because the derivative is negative. Sometimes it's plus the derivative value, and then if our given number is less than our nice number, then delta x would be negative. But this one's not quite as easy to do in our heads as, hopefully I'll pick one that's fairly easy to do for you in your head. But negative 1/4 times 0.2, or 1/4 would be 0.25, 0.2. That would be what? Can you do that? Okay, so actually 0.05. Now watch the decimal values. That's not too bad to do in our head, but so 0.5 minus 0.05, we can get a pretty good approximation then. 1 divided by 2.2 would be about 0.45. So using the linear approximation, recognizing what type of function we have, taking the derivative of that, finding a nice number to work with. And now all of this stuff, all of these formulas and everything, you'll need to know in your head. So not on a piece of paper, no note cards allowed. But think about how we get this. That would be almost like looking at the equation of a line, kind of that idea. But, okay, questions on the linear approximation? This would be one possible problem of the 13. Now, 13 problems total, so, and definitely we won't have a problem of every single type of problem we looked at. That might take you a week to get that test done, but at least a little bit of everything. Probably there might be one or two concepts that we don't see on the test, but you need to overstudy so you're ready for those. I'm not going to tell you which ones not to worry about, but okay. That was one of the first things we looked at in this unit. Next up, we looked at Newton's method to approximate the solution to an equation or to the zero of a function. And, well, for instance, if we have something like this, well, we are not able to find the exact value. If it's just a quadratic, we could find the exact value either through factoring or quadratic formula or something like that. But with a cubic, we don't have the cubic formula. There actually is a cubic formula, but it's really, really wild. We're not going to worry about that. But just to show you Newton's method of approximating what the solution to this would be. And I will also say continue the process until probably like the worksheet, until two successive approximations differ by less than 0.001. So you may want to round to at least 4 decimal places instead of just 2 or 3, so we have the accuracy we need. But what we've got to do first of all is pick a good starting point. And that usually means find, well, maybe f of 0, maybe f of 1, maybe f of 2. It will vary depending on the function. If we look at f of 0, we would have what?
1.
Okay, 1. And that's probably a real good place to start. F of 1. That's also 1. Well, are we guaranteed there's a 0 in between 0 and 1? Not necessarily. How about f of negative 1? What's that one? Also 1? Be negative 1 plus 1 plus 1. So somewhere in there, there's probably a 0. Any one of these 3 values would be a good starting point. X equals 0, x equals 1, x equals negative 1. None of them jump out and say, I'm the best one. Some of the functions we work with, 0 might be a better choice, 1 might be a better choice.
Wait, f of negative 1, it's negative 1, isn't it?
F of negative 1 is positive 1.
Does that make sense?
This is negative 1 minus negative 1 would be plus 1, and then plus another 1.
Oh, I
Okay.
see that.
So, when something like this happens, probably the middle one would be a good one to choose. However, if you choose x equals 1 as your initial value, or even x equals negative 1, you would not be wrong. You just need to possibly do a little more work to get our values a little closer, or the successive approximations to be close enough. So I guess we would say let x of 1 equal 0 would be our initial choice. Now, the formula here for our next approximation, do you remember what that will be? It's the initial x value, then minus,
Function over the derivative.
right, the function evaluated at our initial point divided by the derivative evaluated at that initial point. Okay. Again, this is something you'll need need to remember. So x sub 2 will have x sub 1 minus f of x sub 1 minus f primed of x sub 1. Well, we've got f of x. We need to show what f primed of x is. Okay. So f of 0 we already calculated was 1. F primed of 0, well, up here we'd end up with -1. That's what makes 0 such a nice beginning choice. The calculations are very easy. And we end up with, well, +1. Well, that would have shown us that x equals 1 would have been a better first choice, but we didn't know that at the time. Just choose. So then we do x equals 1. And go through the process again. I'm not going to go through every single one, but at least these, we kind of already have the values. F of 1, again, we said was 1. F primed of 1, well, that one's not too hard to calculate. 3 minus 1 would be 2. So x sub 3 ends up being 0.5. Then, next up, we would use 0.5 as our x. And this is where it starts to get a little more complicated with the calculations. But that's where a calculator comes very handy. Make sure you're entering the numbers correctly into your calculator. When in doubt on fractions, put parentheses around your numerator, put parentheses around your denominator. You can't have too many parentheses, but you can have too few parentheses. You can easily make a mistake just plugging it into your calculator. So, and just continue doing that time and again until the difference between your two of your approximations is 0.001. And that would get you close enough. So, questions there? Next topic was optimization. And we've spent quite a bit of time on different types of problems here. In fact, we had 4 different worksheets on just optimization. A lot of different types of problems, though. But the idea was pretty much the same. What we need is a function that we maximize or minimize. Now that function, notice it says function, not just any equation. That function usually comes from a formula, some type of relationship between the quantities we're being described. And if we're trying to maximize the area of a rectangle, then we'd start out area equals length times width. But then we'd need to have some other information to give us a relationship between length and width. A lot of times that meant perimeter or kind of an adjustment on the perimeter. If we had a rectangular fence or fence going around a rectangular field, and then we want to cut the area in half with another fence, then the total amount of fence would actually be 2 of the lengths, and we call that X, or you could call that Y, it doesn't really matter. And then, yeah, we'd have 3 of the widths. So our amount of fence or length of fence, I usually say perimeter, but that's what we would be given, would be 2x plus 3y in this case. And then we could solve for one of them. I guess we could, since we're doing x and y as length and width, we make the area x times y. Solve for either x or y here, and then substitute it in back into the area formula. And we would then have a function of just one variable. Maximize that function, derivative, set the derivative equal to 0, and go through that process. But really, these are the key parts to the optimization. Finding the equation that we're trying to maximize or minimize, and then turn that equation into a function based on what else we're given, what specifics were given in the relationship between the variables. And again, first worksheet, intro to optimization, we looked at a few of these. Then optimization techniques, we looked at getting a flat piece of cardboard, cutting out the corners, trying to maximize the volume after flipping up the sides. Okay, so in that case, volume would be length times width times height. We would say let x represent the size of the squares being cut out. As we fold those up, h would actually be represented by x. And then, well, we would be given the size of our initial sheet of cardboard. Maybe it's 10 feet by 12 feet. That'd be a pretty big box by the time we get done. But what do we do with the 10 and the 12 once we're looking at the volume of this box? Okay, the 12 side would represent this, but when we cut out the corner and fold up the box, okay, this would be the length of the box. L would be 12 minus 2x, and then the width would be what?
Also minus 2x.
Okay, the 10 minus 2x. So our volume function then, all of these would represent or turn the volume into a function. Length, well, length times width times height, and got the volume in terms of just the one variable x. Probably before we want to take a derivative, we want to multiply all that out. Then you can take the derivative, set it equal to 0, and the whole optimization process there. Okay. Questions on that? Other optimization problems we looked at. A closed circular cylinder I guess spell check worked pretty good there. Know the volume of that. Volume of a closed circular cylinder is what?
You think we know that?
We've looked at that one quite often. Yeah, hopefully will come back to you.
Are we gonna need to know that?
Yeah. Now, some of these a little more odd-shaped ones, I'm not going to make you know, but we worked with the circular cylinder enough, volume of pi r squared h, and surface area. Okay, do you remember that one?
Yeah.
The lateral surface area, the the curved part was what?
2 pi r.
2 pi r h. Now, if you forget, just think of, take your cylinder and slice it down the middle and lay it out. Well, it's just a rectangle. The length of that rectangle is the circumference, and then the width of that rectangle would be the height. So that's one way. Sometimes there's some little memorization tools you can use if you forget exactly what it is. You can kind of figure it out that way. And then don't forget, if it's closed, that means there's a top and a bottom. So we'd have 2 of the circles represented by pi r squared, top and bottom. Now, if something is open, an open box or an open circular cylinder, then we only have the bottom to work with. Surface area would only be the bottom, not the top as well. But if it's closed, we'll have 2 of those. Let's see. Now, I may throw something like a 24-inch wire is cut into 2 parts, and one part is shaped into a square and the other into a circle, something like that. But there again, I'm not going to throw you a regular octagon. If I throw you something like that that's not quite normal, I would give you the area formula on that. But rectangles, squares, circles, circular cylinders, boxes, you should be able to figure out volume and surface area from there. But any of the other little stranger volumes or surface areas, I won't ask you to remember those. So that's pretty much the idea on optimization. Whether we're maximizing volume given the surface area or minimizing the surface area given the volume, well, the basic procedure is pretty much the same, but a lot of the details differ by what formula we have. So, any questions on optimization? Next up, we looked at the related rates, how one quantity changing affects another quantity in a certain equation. And we looked at a lot of different types of problems with this. Again, circles, spheres, rectangles, but more of the problems ended up being triangles, and especially right triangles. Some of the problems were good homework problems, kind of like on the applications as well. Good homework problems, but a little more difficult than what you would see on the test. But many of these problems are pretty straightforward. Getting the equation set up right, and a lot of times it ended up being a squared plus b squared equals c squared. Figuring out which parts we knew, which parts were variables, that was the key there. But whether we have a runner on a baseball diamond or an airplane flying horizontally at a certain altitude, or cars leaving a certain point, one going north, one going east, forming that right triangle. I mean, we looked at a lot of different setups, but it ultimately came back to the Pythagorean theorem, setting that up. Let's see. And, well, we also looked at little bit more complicated problems with the volume of a sand pile. As more sand was piled on top, the volume formed a cone. Again, something like that, I would give you the formula for the volume of a cone. I don't even remember that one. I have to look that one up, so I'm not going to require you to learn that. But the idea behind it still, get your equation, lots of relationships between maybe the radius and the height, or in the Pythagorean theorem, maybe a relationship between x or a and c, or maybe we know one of the particular sides, one is constant and the other two are variable. So that's really a lot of working with this. And let's say we have a ladder sliding down the side of a building, sliding at a rate, sliding down at a rate of, say, 0.2 feet per second. And let's say it's a 25-foot ladder. Well, in this case, the ladder does not change the length. 25 foot remains constant whether it's here or whether it's laying flat on the ground. But definitely the x and y change. Now some of the problems, all three of the sides were changing as time went on, so that's one thing you got to figure out. Related rates, take the derivative with respect to t, and we'd have 2x dx by dt, 2y dy by dt, and what's our derivative of 25 squared? Okay, 0. That's a constant, so derivative of constant. Now, what does the 0.2 feet per second represent? Okay, dy dt. Right, that's changing in the y. And what else do we need to think about here? Okay, it's going down, so that would represent a negative rate of change. Y is decreasing over time. And we see that a little bit more after we start looking at the graphing part of this chapter. But since y is decreasing, dy by dt will be negative.
And then you will ask to find dx over dt when
the
x equals in a...
Correct. The question would be, what is the rate of change of the horizontal, or somehow worded, find dx by dt when we know either x or y, where x is, let's see, 5 feet.
X equals 5.
Yeah, 5 feet from the building. Well, we could find y from our original equation. If x is 5, x squared plus y squared, 5 squared plus y squared equals 25 squared. We could find out what y would equal. So we'd have y, we'd have dy by dt, and we'd have x. That will allow us to find dx by dt. So related rates, just a lot of different types of problems dealing with that. So again, we'll probably have 1 or 2 of those problems of the 13 total, not all 13, but that'd be a fun test, wouldn't it? All 13 related rate? No, that's not going to happen, so breathe a sigh of relief. But at least 1 or 2 of those. Questions on those? Well, after we got through the related rates, I think you probably enjoyed Chapter 8 a little bit more.
Yes.
Working with the graphing and all the details that go into that. First, we talked about critical points and maximums, minimums. Now, the first worksheet on this, we talked about not just what we look at with graphing with the relative or local maximums and minimums, but this first worksheet we looked at absolute maximums and minimums over a certain interval. And if that interval was a closed interval, then those maximums and minimums could occur at the endpoints as well as at the critical points. So you got to find your critical points, then test your endpoints as well as your critical points in that interval. Some of the critical points we found were not in the interval given, so we'd throw those out. But the largest function value would be our maximum, the smallest function value would be our minimum. So that could occur either at the endpoints or at the critical points. Now, beyond that worksheet, we pretty much limited it to just our critical points. And where is a function increasing or decreasing? What would we do to find that? What would we look at? Okay, first derivative. If the first derivative is positive, it would be increasing. The function would be increasing. And first derivative be negative, first derivative, then the function would be decreasing. So the first thing we'd do there is find our critical points, most often where the derivative equaled 0, but once in a while where the derivative was undefined. Keep that in mind. And then find the intervals where it's increasing, where the derivative is positive, where the derivative is negative, and identify those intervals. Also, this helped us to find the relative or local maximums and minimums. Some material call them local, some material calls it relative, so I'll just throw both terms out there. And that's going to occur possibly at the critical points. Just because we have a critical point doesn't mean it will be a maximum or a minimum. But if it is a maximum or a minimum, it will be at a critical point. Don't think too hard on that expression. One direction works, but the other direction doesn't. But from the increasing and decreasing intervals, we can tell whether it's a maximum or a minimum. Say A and B. Here's our critical points. Derivative was positive up to A, then negative past A, then positive past B. Well, at A, up to A, we'd have an increasing. Between A and B, we'd have a decreasing. After B, we'd have an increasing. So, would we have a local maximum?
Yes.
At
A.
Okay, local maximum would be at A, increasing and then decreasing. And what could we say about B?
It's a local minimum.
Local minimum, decreasing and then increasing. So from that, we can kind of identify a little more detail on our critical points, on the graphing, and we kind of pulled all of that together at the end where I started having you graphing some functions, going through all those long procedures. But also, I did throw out some suppose f of x is such and has critical points at such numbers. The derivative is less than 0 on this interval, greater than 0 on this interval, either what's happening at the critical points, or maybe a problem like graph a function with these conditions.
So when you're saying what's happening at a critical point, are you just wanting to know if it's a max or a
Yeah.
Okay.
Is it a maximum? Is it a minimum? Is it neither? Okay, so basically, given the information, we can still do this. We really have less work to do, but it's kind of more work to figure out what it's telling us. So a little bit different than given the equation of a function and going through the process. So make sure you can do that. And then with that as well, we talked about concavity. And concavity deals with the second derivative. If the second derivative is negative, what do we have?
Downward concave.
Okay, concave down. If second derivative is positive, we have concave up. So again, similar to the increasing and decreasing, concavity questions would be where is it concave up, where is it concave down, but we look at the second derivative rather than the first derivative. And some general questions as well. Suppose a function has a second derivative positive over some interval. What's that graph going to look like? So positive second derivative would be concave up over that interval.
Are we going to actually have to draw the graphs or just tell you about
Possibly drawing the graph. Given these conditions, draw a graph that fits it. So. So now, pulling all of this together, we looked at some graphing in detail. I will not say, here's a function, graph it in detail. The questions are long enough without having that, but those types of parts of the problem will show up in individual problems. So essentially, in the graphing in detail problem 1 to 3, I say identify intervals where it's increasing and decreasing. That would be one problem on its own. Identify local maximums and minimums. That would be a problem on its own. Identify intervals of concavity and inflection points. Again, those would be individual problems rather than one huge problem with 4 or 5 different parts. So don't worry about being able to graph something from scratch. But you should know the details of it, the parts of it. Now the other thing that we covered, we looked at asymptotes, graphing with asymptotes, graphing with holes and asymptotes. I will have specific problems saying find the horizontal and vertical asymptotes, but I'm not going to have you graph something with those. And I'm not going to say identify where the holes are in the graphs, but basically it's kind of with a vertical asymptote or with a rational function, you could have 2 possible parts to it. Let's just say x minus 2 over x squared minus 4. Ultimately, we look at where the denominator is equal to 0, and we would get x is plus or minus 2. Well, then it depends on what's in the numerator, whether both of these will be vertical asymptotes or one of these will actually be where a hole is in the graph. We only have one vertical asymptote here. And to be able to find that, you'd have to show the factors of the top and bottom. And because of the x minus 2 in the numerator as well as in the denominator, the vertical asymptote would be what? Okay, x equals negative 2.
And then, in other words, at positive 2, it does not.
At positive 2, x equals positive 2, that would not be in the domain, but if we tried to graph it, it would be just the hole in the graph rather than a vertical asymptote. I'm not going to ask about the holes in the graph, but basically you'll know what you're doing with that from this and only get that. And also, it's not just the vertical asymptote is negative 2. Negative 2 is a number, not a vertical asymptote. It's got to be x equals negative 2 to show the vertical line is x equals. Horizontal asymptotes need to be the equation y equals whatever number, not just the number. Okay? And in fact, the horizontal asymptote in this one would be what? Okay. Would be what? Okay, y equals 0, not just 0. Degree in the numerator is less than the degree in the denominator, so just y equals 0. If it was the same, what would we look at?
Look at the ratio.
Okay, look at your leading coefficient ratio, and that would be your horizontal. Okay, and one last thing we'd looked at, but I'm not going to have anything on the test, no oblique asymptotes to worry about. Again, good homework problems, but not good test problems. That could be the test all in itself. I want to see if you know it, some other things as well. So, okay, like I said, 13 problems scattered out from all of these topics. You can have as long as you need to take the test, well, within reason. I'm not going to let you have 8 hours on the test, but you shouldn't need that much. But probably try to allow yourself at least an hour and a half, just in case. Most of you probably get it done in an hour, but I don't want time to be a factor. Any questions?